Hello and welcome to Chemistry C1 revision. An atom is the smallest part of an element that can take place in a chemical reaction. Most of an atom is actually free space with a small dense positively charged nucleus, surrounded by negatively charged electrons. The atom is in fact made up of even smaller particles arranged in a particular fashion. There are three main particles to be considered: the proton, electron, and neutron. An element is any of 118 known substances that contain one type of atom only, which cannot be broken down chemically. The clue to spotting elements is that all the atoms are the same irrespective of the bonding between them. A mixture is a substance containing two or more chemicals that can easily be separated by physical means, for example boiling or filtration. The atomic number is the number of protons in the nucleus of an atom. The atomic number also gives the number of electrons in orbit around the nucleus. The overall charge of an atom is 0. The number of protons is equal to the number of electrons. The mass number is the sum of protons and neutrons in the nucleus of an atom. The periodic table is the simplest and clearest method of classifying elements so that they can be easily seen. It presents a method of allowing predictions on the behavior and properties of known and unknown elements based on their position within the table. The period number is the number of shells of electrons present in the atom and shows which row of the periodic table the element occurs in. These elements in group 7 of the periodic table and comprise the following: fluorine, chlorine, bromine, and iodine, being elements in the same group that have very similar chemical properties, but their physical properties change as the group is descended. These are sometimes called the rare or noble gases and occupy group 8, also known as group 0. They are generally unreactive and therefore commonly known as the name inert gases. More than 3/4 of the elements in the periodic table are metals. These are usually elements in group 1, 2, and 3 of the periodic table. Metals share certain common physical properties in that they are solids at room temperature except for mercury, which is a liquid. They usually have a high melting point and a high boiling point. They are normally shiny when polished. They can easily be hammered or bent into shape or pulled into wires. They are good conductors of heat and electricity when solid or liquid. All gaseous non-metallic elements and the halogens, apart from the noble gases, exist as diatomic molecules. For example, F2, O2, Cl2, and N2. Crude oil is formed from the long-term effects of heat and pressure on the deposits of microorganisms that deposit on the seabed. The oil itself is formed between layers of porous and non-porous rock, where it can be tapped and extracted by large drills. Natural gas is often formed in conjunction with oil, and this is often seen being burnt off the top of oil platforms. The oil that is brought to the surface is called crude oil. Crude oil is a mixture of basic organic molecules called hydrocarbons. The larger molecules produced by fractional distillation are not particularly useful as chemical reagents and therefore may be broken down to form smaller, more useful ones, normally a mixture of alkanes and alkenes. This process is carried out using a catalyst in the absence of oxygen and is at relatively low temperatures. It is known as catalytic cracking. A hydrocarbon is a molecule containing carbon and hydrogen only. These hydrocarbons have different chemical and physical properties due to their different molecular masses. This means that the components of crude oil can be separated using a difference in their boiling points. The separation is achieved by fractional distillation. The forces of attraction between these molecules determine the boiling points of the hydrocarbons. Intermolecular forces between large hydrocarbons are higher than those between small molecules. This means that the energy required to separate the larger hydrocarbons is greater than the energy required to separate smaller molecules. The boiling point of large hydrocarbons is therefore higher than that of a smaller one. The size of the hydrocarbons defines the use of that particular fraction extracted from the crude oil. Methane, liquid petroleum gases, petroleum, kerosene, diesel and heavy tars are all extracted from crude oil. As the molecules in the fractions increase in size, so does the viscosity and boiling point, whilst flammability decreases. Hydrocarbons may be written in a number of different ways to describe the actual number of atoms in the molecule, or to give an indication of how these atoms are attached to one another. The molecular formula gives the actual number of atoms present in the molecule. For the simplest group of hydrocarbons called alkanes, all members have a molecular formula which fits the general formula for the group, CnH2n+2. The displayed formula gives the arrangement of atoms in a molecule, identifies which atoms are bonded to which, and shows the specific presence of multiple bonds and specific groups. For example, methane has a symbol formula of CH4, where N is 1. Ethane has a symbol of C2H6 when N is 2. Obviously, fossil fuels can be used as a source of energy. Fossil fuels are not pure substances in that they contain a range of different materials, but mainly, but not exclusively, carbon. When these fuels are burnt, energy is released, but it is in a range of other pollutants: carbon monoxide, sulfur dioxide, and oxides of nitrogen. These pollutants are responsible for a whole range of environmental problems, ranging from the greenhouse effect to acid rain and global dimming. Intermolecular forces between large hydrocarbons are higher than those between smaller molecules. This means that the energy required to separate the larger hydrocarbons is greater than the energy required to separate smaller molecules. The boiling point of large hydrocarbons is therefore higher than that of a smaller one. Hydrocarbons burn very readily in excess of oxygen to produce carbon dioxide and water in a process commonly known as combustion. In order for combustion to occur, there needs to be a fuel, a heat source, and oxygen. The result in the release of large amounts of energy. However, in the absence of oxygen, or unlimited amounts, carbon monoxide and carbon are often formed. The benefits of complete combustion are that less soot is made and more heat is released, and the poisonous carbon monoxide gas is not produced. Greenhouse effect is the term for the role the atmosphere plays in helping warm up the Earth's surface. The atmosphere is largely transparent to incoming short-wave infrared radiation, which is absorbed by the Earth's surface. This radiation is then re-emitted at longer infrared wavelengths, but is reflected back by gases such as carbon dioxide and methane. The amount of carbon dioxide in the atmosphere has been increasing because of the amount of fossil fuels, such as gas, oil and coal, being combusted. Warming of this magnitude could alter climates, affect crop production, and cause sea levels to rise significantly because of the melting of polar ice caps. Acid rain is a form of air pollution. It forms when oxides of sulfur and nitrogen combine with atmospheric moisture to yield sulfuric and nitric acids. The pollution may also take the form of snow or fog, or be precipitated in dry forms. Industrial emissions have been blamed as the major cause of acid rain. The severity of its effects have long been recognized in local settings, as exemplified by the spells of acid smog in heavily industrialized areas. Acid rain has eroded structures, damaged crops and forests, and threatens life in freshwater lakes. particles released into the atmosphere from the combustion of hydrocarbons potentially lead to a problem known as global dimming. Water drops in the air become seeded with air particulates. Seeded water droplets are more reflective than normal droplets, and such reflect more solar radiation back into space. The net result is that less heat reaches the Earth's surface. Many fuels have their sulfur content reduced before combustion. This is particularly relevant to low sulfur petrol. Other solutions included the removal of sulfur dioxide before it enters the atmosphere. Power stations which burn fossil fuels have chimneys lined with chemicals to remove the sulfur dioxide. However, in the absence of oxygen or unlimited amounts, carbon monoxide and carbon are often formed. The benefits of complete combustion are that less soot is made and more heat is released, and the poisonous carbon monoxide gas is not produced. Greenhouse effect is the term for the role the atmosphere plays in helping warm up the Earth's surface. The atmosphere is largely transparent to incoming short-wave infrared radiation, which is absorbed by the Earth's surface. This radiation is then re-emitted at longer infrared wavelengths, but is reflected back by gases such as carbon dioxide and methane. The amount of carbon dioxide in the atmosphere has been increasing because of the amount of fossil fuels such as gas, oil and coal being combusted. Warming of this magnitude could alter climates, affect crop production, and cause sea levels to rise significantly because of the melting of polar ice caps. Acid rain is a form of air pollution. It forms when oxides of sulfur and nitrogen combine with atmospheric moisture to yield sulfuric and nitric acids. The pollution may also take the form of snow or fog, or be precipitated in dry forms. Industrial emissions have been blamed as the major cause of acid rain. The severity of its effects have long been recognized to remove oxygen from the ore to produce molten iron. The blast furnace is a tower into which is fed iron ore, coke and limestone. Hot air is blown into the furnace, causing the coke to burn much faster and at a higher temperature than normal, approximately 1500 degrees Celsius. Heating the ore alone. This is the cheapest method of extracting metals, but it only works with the most unreactive metals at the bottom of the reactivity series, like gold and silver. Reduction. The metals in the middle of the reactivity series, such as zinc, iron, lead and copper, cannot be attained simply by heating them. These metals are less reactive than carbon, and as such they are obtained by heating with carbon directly or reacting with carbon monoxide. The carbon reduces the metal oxide, producing molten metal. Electrolysis. Reactive metals that cannot be extracted from their ores by reduction with carbon are produced by passing a current through their molten ores. Aluminium is extracted by electrolysis of molten aluminium oxide. The iron produced in the blast furnace is molten due to the high temperature and being denser than the contents of the blast furnace drops to the bottom and of the furnace where it is tapped off. However, this pig iron is impure and brittle, and it contains a lot of carbon impurities. These are removed by blowing air through the molten iron, which converts carbon to carbon dioxide gas. This produces a product called steel. Iron also contains impurities, the main one of which is sand, which is also known as silicon dioxide. This is removed by the addition of calcium carbonate, also known as limestone, which reacts with the sand to form a molten product called slag. This also falls to the bottom of the furnace and is tapped off. Usually floating on the surface, is more dense than molten iron. Cooled slag is used for road building and fertilizer.